Okay, so coproducts is one notion that we're going to need to understand the idea of OR. And then the other notion that we're going to use is this notion of the direct image of an arrow. Now, there's various equivalent ways to define this. I'm using the approach given on page 336 of Levere's book, Conceptual Mathematics. And so we define the direct image of an arrow f from A to B as a subobject of B, which we call IMF. And we think of this as a monomorphism from an object we call f, open square bracket A, close square bracket, to B. And we define this as the subobject of B, which is such that f is in IMF, and for any subobject J of B, we have that f is in J implies IMF is contained in J. So in a way, we can think of IMF as the kind of minimal subobject of B, which has f in it, okay? Because any other subobject J of B, which has f in it, has the property that IMF is contained within it. So the question, as ever, is what does this kind of thing look like in set to the power of C? And I should mention there are various other ways one can construct this direct image, but I like this one because it's very sort of arrow-centric in general. I mean, one can talk about this kind of thing, at least one can use this kind of definition in any category. Anyway, what does this thing look like in set to the power of C? Well, we have here this direct image lemma. So what it says is that if we want to treat IMF as an inclusion monic, then of course its components, like its ETH component, is going to be an inclusion function. And the important thing is the structure of F, open square bracket A, close square bracket. And this result tells us that the set of E figures of such a thing is just going to be the set of F of E of alpha, such that alpha is an E-type element of A. So it's really very self-explanatory. I mean, this is pretty much how you think of a direct image. If we just think of one component of this, it's pretty much what the direct image of an arrow looks like in the category of sets. It's the kind of collection of stuff in B that has something sent to it under F, okay? And just taking the kind of E figures related to that gives us the kind of E figures of the source of this inclusion monic, IMF. So how can we prove that this kind of result holds? Well, obviously we're supposing IMF is an inclusion monic. And then we sort of apply this definition, but this definition basically says that we better check that IMF satisfies various properties with respect to these subobjects J of B. So, you know, in theory, we should check over all of the subobjects J of B. But actually, we know that for any kind of class of equivalent subobjects of B, there's always one kind of inclusion monic that's sort of representative of that. So it'll suffice to check that our IMF satisfies this kind of property for every inclusion monic J into B. So we can just consider this condition but apply to the inclusion monics. So let's consider such an inclusion monic J into B. Now we can consider IMF to be the direct image of F when we have that F is in IMF And also, for every such inclusion monic J into B, we have that if F is in J, then IMF is contained in J. So this is the complicated bit, because this is involving kind of comparing with all these different inclusion monics J. So the question is there another way to say F is in J? And indeed there is. This is a kind of result which we've already come across. So we've already established, in fact, it might be in, well, I'll dig out the result in a moment, but the important thing is that when this J is an inclusion monic, we're going to have that F is in J if and only if F subscript E of theta is in capital J of E for each theta in capital A of E, and for each object E of the category C. So this is actually our really important connection. Now, how do we get at this kind of truth? Well, we already discussed this idea as it came up when we were proving the containment lemma. So I've just highlighted it, a sort of different version of it here. So if you look back at the containment lemma, you can see an argument. I mean, this basically is the same kind of idea. It's just we're using different symbols here. So you can look that up. So yeah, we have this result here, that F is in J, if and only if F sends every theta to something in this set, capital J of E. And then an equivalent way to say this is that the set of Fe of theta, such that theta is in capital A of E, is always contained in capital J of E for each E. And now notice that this set on the left here is just precisely what we've been calling F open square bracket A close square bracket of E. And so basically we have that F is in J if and only if F of open square bracket capital A close square bracket of E is contained in capital J of E for every object E of C. And then by the containment lemma, you know, since this kind of thing is just a sort of set of E-type figures of IMF, and this holds for every E, this is equivalent to just saying that IMF is contained in J. So we've now shown that for any inclusion monic, we have that F is in J implies IMF is contained in J. Now, the only other thing we need to do to show is that F is in IMF, and that's also quite easy. So using the, well, I mean, these two sets are actually the same. We know that F open square bracket A close square bracket of E literally is this orange set on the left here. So clearly this orange set on the left is contained in F open square bracket A close square bracket of E for each E. And then again, the containment lemma gives us that this means that, well, and then this means that F is in IMF, which is what we wanted. Okay, so we've basically shown that, yes, we can make the directive image of F in this kind of form. We can have it as an inclusion monic into B, where this set of E-type elements of the source object is just the set of kind of images of E-type figures of A under F, which makes sense because this thing's called the direct image, okay? So basically, once again, we see that direct images in set to the power of C are just sort of high-dimensional analogues of what they are in the category of sets.